Hey, good morning, everyone. Let's continue with our talk of chapter 6.
Mic testing, check one. Okay, that clears it up. Okay, so as I was saying, let's continue with chapter 6. We introduce the transfer function. And brief recap. Transfer function describes the working of a circuit. We don't know what is inside the circuit. We don't really care how it does it. We only want to know what it does. And that is what the transfer function describes. It literally just states how the input is being transferred to the output. So it is a ratio of the output voltage to the input voltage, noted by the letter H. It's a function of frequency. Again, the title of this chapter is Frequency Response. So we are going to look at circuits and see how they change their outputs depending on the input frequencies. So H of F, the transfer function H of F, means it's a function of frequency. It's describing what the circuit is doing to the input signals based on the frequency of the input. It's a ratio of voltages, and so it is simply V out divided by V in, no units, it's dimensionless. And all are complex quantities, all are phasors. And as such, the transfer function has magnitude. So H of F has magnitude and it has phase. It has magnitude and it has phase. It basically describes the operation of that circuit. That circuit is going to be a sealed box to us. Okay. So based on that, let's look at an example problem. This is also the problem that is there in the homework that is due tonight. The homework, there's only two questions on there. One is a short answer question. The second one is the problem, and that problem is exactly the same as what we're going to solve in class. Okay. So the transfer function of a circuit is given to us in graphical form. Okay. It's graphical form. First one on the left gives us the magnitude of H of F. Second one on the right gives us the phase. We don't know what the circuit is. We don't know what it does. There's no name given to the circuit. There's no circuit diagram, but we don't need to know it. And that is the point. That is the point. If you know the transfer function of a circuit, you can design it as a kind of off-the-shelf building block. Okay, you can design circuits using these as building blocks. So we are asked to find V out of T, again, output voltage as a function of time, V out of T, if the input voltage is given by this expression. V in of T has three components. So let's take a look at that expression. Find V out of T if V in of T is 3 plus 2 cos 2000 pi T plus cos of 4000 pi T minus 70 degrees. First thing we notice, it's made up of three independent quantities. It has three components. The input signal has three different components. Okay. 1, 2, and 3. And the reason they are stated as separate with just a summation is simply because the frequencies are different. The frequencies are different. Remember chapter 5, I said in order to combine two or more signals or waveforms together, the frequencies must be the same. If the frequencies are not the same, you cannot add or subtract those waveforms. You simply write it out as a sum. In this instance, the plus sign is acting or behaving like an and, the word and. So input signal V in of t is comprised of 3 and 2 cos 2000 pi t and cos of 4000 pi t and another component and another component, so on and so forth. Does that make sense? Right? There is a summation sign, there's an addition sign in there, but mathematically speaking, we cannot add or subtract if the frequencies are not the same. So in general terms, the purpose of the plus sign is simply and, the word and, A-N-D. That's what it's doing. So once we have a signal like this, break it up into individual parts, V in of t, V in 1, V in 2, V in 3. We write out the individual ones and we extract all of the information, meaning we extract the peak values, the magnitude, the frequency information, and the phase angle. For V in 1, it's a constant value. It is not a function of time. There is no t in that expression. It's not 3t. It's simply 3, meaning it's a constant flat DC value with a value of 3 volts. So if there is no frequency, it is DC. Frequency F is 0. Excuse me. V in 2 is 2 cos 2000 pi t. The frequency for the second component, 1000 hertz. Omega is given, omega divided by 2 pi gives you 1000. So again, omega is 2 pi f, so f is omega over 2 pi. We want the frequency information because the graphs are given in hertz. If they were given in omega, we would need omega information. Okay. So V in 1 has a frequency of 0, V in 2 has a frequency of 1000, and V in 3 has a frequency of 2000 hertz. Then you write down the phasors for all 3 input quantities. Again, H of F is given to us. V in is given to us. We just need to find V out. Okay. And these are all complex quantities. These are all phasors. And so we're going to perform simple algebraic calculations. So we write down the phasors, V in 1, V in 2, and V in 3. First one, of course, it's a DC, so it doesn't have any phase, it doesn't have any angle. So 3 with an angle of 0, V in 2, 2 with an angle of 0, and V in 3 is 1 with an angle of minus 17. So far, so good. Any questions? Okay. Then here's the important part. We want to know how the circuit behaves at any given particular frequency, which is described by these charts right here. Now, the ones that are of interest to us are 0, which is right here, 1000 and 2000. So that's V in 1, that's V in 2, and that's V in 3. So for each particular input frequency, we extract the information about the magnitude and the phase of this circuit or this network, and then write out the transfer function at that particular frequency. Okay. F1 is 0, F2 is 1000, F3 is 2000. So we want to write 3 values. H of 0, H of 1000, H of 2000. The value of the transfer function at F1, F2, and F3. Make sense? Right? So H of 0, H of 1000, H of 2000. We write down both magnitude as well as phase. Magnitude for the first one at 0 is 4. And of course, the angle also is 0. Second one, it's 3 right there. And then 30 degrees. So this is 1, this is 2, and this is 3. Here, this is 1, this is 2, and this is 3. That's it. You're simply reading the numbers off the chart. And then we apply our equation. H of f is V out over V in. So V out is H of f times V in. Plug in the values and perform the calculation. That's it. 4 times 3 gives you 12 volts. 3 angle 30 times 2 angle 0 gives you 6 with the angle of 30. And V out 3 would be 2 with an angle of minus 10. Minus 10. Your final answer should be in the time domain because that is what is being asked. You're asked to find V out as a function of time. And so total V out as a function of time requires you to write the expression in the time domain. So you perform the inverse phasor transform. 12 volts remains 12. There's no function of frequency. 6 angle 30 becomes 6 cos of F2, 2000 pi. Frequency does not change. So 2000 pi t plus 30 degrees, and V out 3 is 2 cos of 4000 pi t minus 10. Again, different frequencies. If your components have different frequencies, you cannot add them. And so your final answer will also be in 3 components. Okay, let's take a pause. Think over all the steps. Let me know if you have any questions. Any questions at all? How long do you think it would take you to solve this problem? 7, 8, 10 minutes? 15 at the most? So the point I'm making is the homework that is due tonight shouldn't take you longer than 15 to 20 minutes. So if you have time right after this class, go ahead and knock it out. Okay, shall we move on? All right. So at the beginning of this chapter, I stated, right, we have to adjust our thinking a little bit. The circuits, of course, will have the normal voltages and currents flowing through it. But from now on, we have to think in terms of a port, meaning a pair of terminals, meaning inputs coming in from one side of the circuit, and you're extracting the output from the other side of the circuit. Okay. Now, the entire chapter, as I said, we are studying frequency response. Frequency response. In the words themselves mean that the behavior of the circuit will change depending on the input frequency, right? The response of the circuit is going to change depending on the input frequency. So which are the components that behave differently at different frequencies? Those are inductors and capacitors. And we can model inductors and capacitors as either open circuits or short circuits, depending on the incoming input frequency. And that comes from the value for the reactance X or in terms of impedance. We can just talk in terms of impedance, okay? So impedance ZL is J 2 pi FL, meaning for an inductor, the impedance is directly proportional to the frequency. For a capacitor, ZC, impedance of a capacitor is 1 over J 2 pi FC, meaning ZC is inversely proportional to frequency. And based on these properties, we can describe the behavior of an inductor at extremely low and extremely high frequencies. Remember, reactance for capacitors and inductors depends on the frequency. The faster the input changes for an inductor, the more it opposes this change, right? When it changes, it opposes that change. So the more it changes, the more it opposes, directly proportional, okay? And so at extremely low frequencies, pointing towards zero or tending towards zero, we can say an inductor behaves like a short circuit, or SC. Like to say SC and OC. And at extremely high frequencies, the inductor opposition increases as the frequency F tends towards infinity. The inductor impedance increases and it behaves like an open circuit. Make sense? Right? Capacitor behaves exactly the opposite, reciprocal of frequency. So capacitor behaves like an open circuit for very low frequencies and behaves like a short circuit for extremely high frequencies. Which, if you remember, steady state conditions from chapter 3, for DC, 0 hertz, of course, is DC. For DC, inductors behave like a short, capacitors behave like an open. And we can use this table to perform a quick rudimentary analysis of any circuit. Okay, we can do a quick and easy analysis using this table. So we're going to study 6 different kind of filters. Well, not 6, well, 1, 2, 3. Well, yeah, 5 and 6 are kind of very similar. Just the circuit configuration is different, but the equations are very similar across the board. So a total of 6 that we will look at, but there will be overlapping similarities amongst all of them. Okay. Filters can be classified broadly using the component that is used to build that circuit. We can call them RC or RL. So if it's capacitor based, we call them RC circuits. If it's inductor based, we call them RL circuits. And then we have circuits that use both of them, and we call those RLC circuits. So we're going to look at low pass filters created using both RC and RL. So like this. And then we're going to look at high pass filters using both RC and RL. So it's a 2x2 cross matrix. And then there are band pass and band reject filters. We will look at 2 band pass filters. Chapter 4, transient analysis. I said if you have one energy storage element, you have a first order differential equation. Hence, we call it a first order circuit. Similar to that, filters also come in multiple different orders. If it's one energy storage element, we refer to it as a first order filter. If it's more than one, second order, third order, fourth order, and so on and so forth. Filter study and filter design is an entirely separate course or subject of study under electrical engineering. Okay, so what we are looking at is just barely the top surface. Okay. All right, so as I said, you're going to study 4 different filters, but there are overlapping similarities across all of them. So let's look at a RC filter first. Okay, RC filter, you have a resistor that is connected in series, and the output is taken across the capacitor. Okay, output is taken across the capacitor. So we can draw the circuit like this. Just because we take the output across the capacitor does not mean that the resistor and capacitor are not in series. sometimes when you first look at these circuits, it's hard to visualize. Hence, I'm drawing it out this way. It's a straightforward circuit. You have a resistor and a capacitor connected in series to a voltage source V in. And you have current I flowing through the circuit. This would be R, and this would be C. And V out is taken across the capacitor. Excuse me, sorry. Now, there is a small derivation in here, but again, derivation is not important. What is important is the transfer function of that filter. But let's do a quick and easy analysis. Let me show you how we can do a quick and easy analysis using our handy dandy table. Okay. So let's model the circuit at F is equal to 0. At F is equal to 0, of course, resistor behaves the exact same way, but capacitor behaves like an open circuit, right? Capacitor behaves like an open circuit. So our V in goes through the resistor, and because the capacitor is open circuit, nothing is going down there. We can simply take output V out as equal to V in. Right? Capacitor is open, nothing is going down there. It's basically the output through that resistor, meaning whatever you give as the input, you will obtain at the output. As easy as that. Okay. There's no other analysis to be performed. Okay. We're not looking at voltages, you're not looking at current, we're not looking at anything. It's simple. It's coming into the circuit, is it coming out? Yes or no? That's it. That's the only thing we're looking at. So the answer here is that yes, because the capacitor is open, we are obtaining something at the output. That's it. When F tends towards infinity, capacitor behaves like a short circuit. And so this time you have a resistor and the capacitor is shorting out the output terminals. What is the voltage across a short circuit wire? You're measuring the voltage between 2 points, and those 2 points are connected together. Exactly the same potential. So V voltage at those 2 points is 0. And that's it, 0. So no output. Again, no mathematical or quantitative calculations required. This is, again, as I said, like calling it the handy dandy table. Use the handy dandy table, and you simply look at the circuit at 0 and at infinity and see V out, is it 0 or is it equal to V in? That's it. Output yes or output no. So in this case, we see that when frequencies are low, you obtain output. When frequencies are high, output is blocked. Yes. If you want to, yeah. But in general, all circuits will have resistances without which we cannot control current. So even if it's just theoretical, we do have resistors in there. Without a resistor in there, you're just saying current is infinite. Okay. So what was I saying? Oh, okay. So low frequencies, output yes. High frequencies, output no. Other words of stating that is high frequencies are blocked, low frequencies are passed. Hence the name of the filter, low pass filter, LPF. Low pass filter. Does that make sense? Right? Low frequencies are being passed, high frequencies are blocked. Hence, the circuit is a low pass filter, LPF. That's the acronym we use in EE, LPF. Okay. The derivation is straightforward. If you're interested, I can, stop by my office. I'll be happy to show it to you. But essentially what you're doing is you find I, total current I in the circuit, and total current I would be R plus ZC. Once you find I, you find V out across the capacitor as I total times ZC. So when you perform these calculations and you rearrange the output terms to give you V out over V in, which is nothing but the transfer function, you obtain this equation. H of F is 1 over 1 plus J F over FB. Okay, F over FB. Where J, of course, is the imaginary number. F is the variable, depends on the value of the input frequency. And FB is a new term. It stands for break frequency or cutoff frequency, and it depends on the values of the components, the resistor and the capacitor. 1 over 2 pi RC. 1 over 2 pi RC. Okay. And in the next slide, I have, I have plots and also have description. Yes. FB is the break frequency. The question being asked is about FB. So FB is the break frequency. It is also known as the cutoff frequency FC. So in our classes, I like to use frequency in hertz. Other classes, other lectures, like let's say you go work for a company, there might be engineers from different schools. They might use omega. You can have omega B, or more commonly, you would have omega C. Omega is 2 pi F, right? So then your omega C, your FB or FC is 1 over 2 pi RC. Omega B or omega C would simply be 1 over RC. 2 pi goes on the other side. 2 pi F gives you 1 over RC. Excuse me. So this is something you should retain and remember. Okay, oftentimes people will talk in terms of frequency F. They might often talk in terms of angular velocity or angular frequency omega. Okay. So these plots here just show how the transfer function, the normalized values of the transfer function will look like for a low pass filter. Okay. Ideal low pass filter will look like this. Right? Sharp drop. You have frequency F on the x-axis, and let's say this could be V out. Okay. Then all values below the break frequency will be allowed to pass, and all values above it would be blocked. Okay. All values below a break frequency. All values below the break frequency will be allowed to pass. All values above will be blocked because it is working as a low pass filter. All right, let's take a pause. Let me know if you have any questions. Any questions? No questions? So what if we take the output across the resistor instead of the capacitor? What do you think would happen? the same circuit. Instead of taking the output across the capacitor, you take the output across the resistor. Chapter 1, currents flowing through in one direction. From a source, it goes from minus to plus. When it enters the resistor, it's positive, exits is negative, capacitor positive, negative, right? So if you take the output across the resistor, you would get something like this. It's the exact same circuit. Nothing has changed. Nothing has changed. The drawing looks a little different, but it's still a resistor in series with a capacitor. No change whatsoever. Okay, no change whatsoever. It's exactly the same circuit. The reason it looks different is because the position of the resistor and the capacitor are changed or flipped, but it's a series circuit. It doesn't actually matter how you connect it. Plus minus, V out. This time we take the output across the resistor. Let's analyze. Handy dandy table. Frequency equal to 0. Capacitor behaves like a open circuit. What is the output? Is anything reaching the output? Yes or no? No, 0. At F towards infinity, capacitor is short circuit. Is input reaching the output? So low frequencies are blocked. High frequencies are allowed to pass through. Hence, it is a high pass filter. The main and important point is the circuit has not changed. You're simply changing the location of your output terminals. The circuit is exactly the same. No difference. It's a resistor in series with a capacitor. If you take the output across the capacitor, it's a low pass filter output. If you take the output across a resistor, it is a high pass filter output. No difference. It's filtering it out. You can think of it in terms of, I'm trying to think of a good analogy. It's just filtering it out and separating it into two parts. That's it. Depending on the size of the component, it's separating it out into two different buckets. That's what it is doing. Okay. The equation for H of F is different. Denominator is the same, 1 plus JF over FB. Numerator has an additional term, JF over FB. The equation for FB remains the same because it is based on the value of the resistor and the capacitor. So it's still 1 over 2 pi RC. So H of F for a high pass filter is different than the H of F for a low pass filter. But for a RC circuit, the FB break frequency is still the same. No change. Okay, no change. A real life application of these simple circuits is inside your audio speakers. Audio speakers, especially like two-way speakers, like the ones that you have in the hall right now. If you have a loudspeaker box, you can have 2 3-way speakers, multiple drivers inside it. Depending on the frequency that it is reproducing, speakers will have different dimensions. Lower frequencies require larger speakers, which are the woofers. And so if you want to send lower frequencies to a particular set of speakers, you would insert a circuit like this, a resistor or a capacitor, and the output of the resistor goes towards the high pass, and then output across the capacitor goes towards the low pass. Okay, so these are the two RC filters. Again, it's not a too complicated circuit in terms of analysis. Okay. Now, of course, if we go in depth and we look at all the currents and the voltages, then yes, but you're not going to do that. If you wish to do that, stop by my office. I'd be happy to show it to you. All right, any questions? Any questions at all? Okay, let's quickly then look at RL. You have RL, where you take the output across the resistor, or you can take the output across the inductor. If you take the output across the resistor, again, remember, it's opposite of the inductor. So taking the output across a resistor in an RC circuit gives you a high pass filter, but in an RL circuit, it gives you a low pass. Okay, it gives you a low pass filter. So if you perform the analysis here at F is equal to 0, inductor behaves like a short circuit. SC. And so low frequencies, you can say V out is allowed to pass through, and at high frequencies, inductor behaves like an open circuit. And so high frequencies are blocked, no output. Hence, this works as a low pass filter. Works as a low pass filter. The transfer function of this RL filter remains exactly the same as the RC low pass filter. Again, there's a derivation where we find the current, then we apply Ohm's law, and you find the output voltage, and that gives you the exact same transfer function as the RC low pass filter. However, the break frequency is now different. Break frequency values depend on the components R and L, becomes R over L, R over 2 pi L. This is different from chapter 4. Chapter 4, we were talking about tau, the time constant. This is not that. This is the break frequency. Okay, this is different. R over 2 pi L. If you take the output across the resistor, you get a low pass. If you take the output across the inductor, you get a high pass, which is what we have here. So again, at F is equal to 0, inductor behaves like a short circuit. So if it behaves like a short circuit, V out goes to 0. And at high frequencies, inductor behaves like an open circuit. And so V out is equal to V in. Hence, it is a high pass filter. High frequencies are allowed to pass through, and low frequencies are blocked. Transfer function for the high pass filter remains exactly the same. FB remains the same for all RL circuits. Okay, let's take a pause. Let me know if you have any questions. Any questions at all? Okay. Look at an example problem. We are given a filter circuit, obviously from our previous 4 circuits, we know what this filter might do. But if you wish to analyze this, we can do our quick and easy analysis. When we do our quick and easy analysis, again, we simply plot in F is equal to 0, F is equal to infinity, and we see what our component is doing at those frequencies. We know capacitor output in an RC circuit means it's a low pass filter. If it's a low pass filter, we know what transfer function we have to use. 1 over 1 plus J F over FB. Now, the question being asked here is, V in of t is given by this expression. Similar to the problem that we solved earlier, and that went very weird. See if this works. All right, I'm gonna give up. All right, V in of t is given as 5 cos of 20 pi t plus 5 cos of 200 pi t plus 5 cos of 2000 pi t. Yes. So we did the analysis right here. Well, the quick answer is, how do I know this is a low pass filter? Is because I just did it. But in any given circuit, we can plug in the component behavior at F is equal to 0 or F is equal to infinity. And we perform this analysis where I can determine whether I receive output or not. So I plug in F is equal to 0, V out, yes or no. F is equal to infinity, V out, yes or no. And depending on my answers, I'll have either 1 yes and 1 no. And I can say for low frequencies, I'm getting output. For high frequencies, no output. So if low frequencies output is yes, then it's a low pass filter. It's allowing low pass filters to work. Okay, so then if we know it's a low pass filter, we know the standard equation, we take our equation and we can write H of F is 1 over 1 plus JF over FB. The component values R and C are given to us. So we can calculate FB. The break frequency for this circuit turns out to be 100 hertz. You plug it in. Okay. Then, first step, right? Find FB as 100 hertz. Then we look at the input. Input again has 3 components. It could have 2 components. It could have hundreds of components. Doesn't really matter. Okay. In real life, of course, hundreds of thousands of components coming in. You design your filters to block out all unwanted components. Only allow the ones that you want to go through. Okay. So if you look at these 3 components, they all have the same magnitude, 5. Plus, they also have the same angle, 0 degrees. So phasors for all 3 are exactly the same. All 3 components. Because phasors do not have any frequency information. Even though the frequencies are different, the phasors are exactly the same. But that doesn't affect how our circuit works or our analysis works. Okay. We simply compare it to the standard expression. We extract information about the peak values, about omega, and about the phase angle theta. So for first component F1, frequency is 10 hertz. 20 pi divided by 2 pi. Omega is 2 pi f. Since my transfer function is given as a function of f, I'm going to need to extract the information about f in hertz. F in hertz. So F1 is 10 hertz. F2 is 100 hertz, and F3 is 1000 hertz. Okay. F1, F2, and F3. It's similar to the first problem, first example. We are extracting the frequency information from the input component given to us, okay, from Vin of t. Now that we have the frequency information, we plug it in. We have f of b, not f of b, sorry, we have a value for fb, you have f1, f2, and f3. You can find the transfer function at f1, f2, and f3. So h of 10, h of 100, and h of 1000. Okay, h of 10, h of 100, h of 1000. You plug in the values for h of 10. It is 1 plus f over fb. F is 10, fb is 100, so you get 0.1j. 0.1j. This is the point again where I remind everyone, you need to be an expert to perform these complex math calculations on your own calculator devices. If you can't do so, it's going to be rough seas. Okay, so 1 over 1 plus 0.1j, or j.1. When you solve that, you obtain the value of h of 10 as 0.99. 0.99 minus j.099. The reason I've taken so many significant figures or just so many decimal places, I just didn't want there to be an error. 0.99, if you round up, you can just state it as 1. But again, as engineers, you want to find actual, precise, accurate values. Okay. And so I just went like 4, 5, 6 decimal places so I can differentiate between each step. That's why I've taken so many decimal points. So 0.990099, and the same thing for j, you get real, imaginary, as close to 1 as possible, which makes sense because my cutoff frequency is 100 hertz. All frequencies below 100 hertz should be allowed to pass through, right? The first input component is 10, which is lower than 100. It should be allowed to pass through without any reduction in its value and its peak values, right? So 0.9950, when I convert it into phasor form or into complex form, with an angle of minus 5.71. Then I do the same thing for h of 100 and h of 1000. You plug in value of f as 100, what do you get? 1. 1 plus j. 1 plus j. Angle of minus 45. And this number is important, 0.707. 0.707. Okay, 0.707 times your input. Okay. And then h of 1000. 1000 is much larger than 100. And so final magnitude drops to less than 10%, 0.09, 0.099. Okay, 0.099. Now you have the transfer function, the behavior of the circuit at each one of these 3 frequencies. Okay, at 10 hertz, 100 hertz, and 1000 hertz. All that's remaining is multiplying with the input voltage, and you find the output at each one of these frequencies. So at h of 10, your output is 4.975. It has dropped a bit from 5 volts. Remember, each quantity has, it's 10 o'clock. If you have to leave, you can leave. I'm going to finish up this explanation. So at 10 hertz, which is far lower than 100, right? Output should pass unimpeded. Yet there is a small drop in the output voltage. Your input voltage is 5 volts, output is 4.975. Hence the reason why I didn't round up. Okay, I want to get very accurate value. So 4.975, angle of minus 5.71. Second, 3.53. And the last one is 0.49, less than half a volt. So from 5 volts, it dropped to less than half a volt. As I said, less than 10% of the input, right? So lower frequencies are being passed through, higher frequencies are being blocked. If I plot these out, I have my 3 points right here. 3 points right here. Those 3 points, basically, one is exactly at the break frequency. The first one is below the break frequency, and the other one is much higher than the break frequency. And you get a function that behaves like a low pass filter. Okay, low pass filter. And final answer, V out of T, you perform the inverse phasor transform or the reverse phasor transform, and you write out your final answer as time domain expression, V out of T. Okay, we'll end class here today. I'll see you all on Monday. I will post information about the quiz sometime later this afternoon. Office hours today are going to be later after 2 o'clock. I'm attending a seminar. So again, I'll send out an email. So hopefully students don't end up wasting their time. All right, I'll bid you a good weekend. See you all on Monday.